Okay, good afternoon, guys. We'll start off the session. Today, we'll be doing Intro to ML and Matplotlib. I'm Shrikar, and together we are Shrikar Babu, Varsha, Priyanka, Srinivasan, and Anirudh Kalyan will be taking the session today. In today's session, we'll be covering a library called Matplotlib. Then we'll move on to introduction to machine learning, types of machine learning. Under types of machine learning, we'll talk about unsupervised learning and supervised learning. We'll talk a little bit about reinforcement learning too. And under supervised learning, we'll go in depth into regression, specifically linear and polynomial regression. And under classification, we'll move through logistic regression. First, let's start off with Matplotlib. Anirudh will take care of Matplotlib now. Anirudh, go ahead.
Hello everyone, am I audible? Hello?
Yes, Anirudh, go ahead.
Yes. So I took a session for pandas last time out on Wednesday, and today I'll be taking Matplotlib, or Matplotlib as we would call it. And so can I have a few reactions to see just to see the interaction level of this audience, please? Any reaction would accept raising hand. All right, fine. So let's get started with Matplotlib. Now, if you are interested to join the session, I'm sure you would have heard of Matplotlib. It is a very powerful tool. That's pretty much. I mean, we are covering all the major powerful tools in Python for data science, and so Matplotlib is an extremely powerful data visualization tool that is almost endless. It's being built on to even today, and it's an open source library, and it just keeps on growing in its size and capabilities. And today will be our attempt to give you a basic fundamental idea on what Matplotlib is and how you can use it to visualize your data. So once again, you have to first ask yourself the question, what data do you want to visualize? So there are certain types of data sets which you can gain very valuable, very powerful insights by visualizing them. But there are also certain other data sets where necessarily visualizing them will not give you a pretty good idea of what we're actually going to like what we want to achieve with it, right? So keep that in mind, because last time I used a serial data set. If you were there with me for the last session, I used a data set which gave information about various cereals in the American food industry. So that we had Fruit Loops and Cocoa Puffs and all of that. If you think about it, and if you remember the data a bit, you don't necessarily gain much insights with graphing or visualizing that per se. So today I'll be looking at a new data set, which is petrol prices in various cities in India. Just a brief introduction before we move on to the crux of this session. Okay, fine. So let us start with what libraries I will be using. Nothing that we haven't seen before in terms of NumPy and Pandas. But here I'm also using from Matplotlib import pyplot as PLT. Now, again, I'll be going through different segments within the same line of code. From Matplotlib, of course, this is your big library. From that, we are importing a sort of sub-library, which we call as pyplot. And since we cannot type pyplot every single time, we are importing it with a pseudonym as PLT. This is similar to using namespace as std in C++ if you have done it before. And of course, we have done the same as with NumPy and Pandas. And I've also imported certain other sub-libraries and the entire library itself to deal with certain commands. So as we can see, it runs. So yeah, as I mentioned before, when we used a serial data set, you notice that we cannot infer much using the graph visualization from that particular data set. So what would you usually use graphs for if you think about it? You would usually use it to find trends. So like you try to find, okay, on X day, your number of COVID cases were this much and it improved here. Or you would think about, I would want to look at the petrol prices where it was before, let us say, a major announcement that is concerning the entire economy. That day before or the day after. Usually it's a stock market which deals with that, but you would usually use graphs to analyze trends. So for that, I'll be using petrol prices across various cities for today's demonstration purposes. So now let's get with the most basic most basic function of Matplot library, which is plt.plot. Once again, I'm using plt as a pseudonym. Ideally, you could be using pyplot, which is the name, but you can name it as whatever you want. But yeah, the plt is what is unspoken, or the unspoken way of using this. Anyways, the most fundamental command to Matplot library. There are so many parameters to the commands that there are almost endless options. So how can you plt.plot, by the way, is the command which will basically plot the graph that you tell into the canvas. So I'm calling this white background as the canvas. What goes here, what goes in the x-axis, what goes in the y-axis, what is your graph, how does it look like, where are the markers? This command takes care of everything. The canvas is basically just the white background at the back. So now let's break this down. This is one very large command. It's a pretty long command, but it's actually pretty easy. Let us get started with this one by one, right? So I have gone through it here, but I'll also go through it with the command itself. So plt.plot 1, 2, 3, 4, 5, 6. Pretty intuitively, if you notice from the graph, 1, 2, 3, and 4, 5, 6 are your x values and y values. So if the graph were to see, if Matplotlib were to read this, it will read it as 1, 4, 2, 5, and 3, 6. So that is the x and the y parameters that will be passing into this function. Now, if that is all I put in this, then you will get a pretty plain graph with a random color and a pretty thin line weight. So what I'm doing, I'm customizing this better. I'm giving it a label, which as of now, it's not useful because I have not put a legend. But when I put a legend, the label comes into play. I'll come into legends a bit later, but just think about that. This just labels the graph. I label it as x plus 3 for the time being.
Excuse me, can you zoom it a little bit your window?
Sure. This is better?
Yeah.
Okay, nice. So okay. So I'm labeling this as x plus 3. Color, pretty self-explanatory. Also notice that there's the American spelling of color. Not the, wherever you see color, it's the American spelling, just a small thing. You find a bug somewhere. Line width equal to 5. That is just the amount of pixels of lines you want to give it. MFC, which actually I've given it as marker fill color. Has anybody have something to say? Okay. And so MFC is the shorthand notation for marker fill color. What is a marker? It is this. So basically, I have given MFC before I've given marker. So what marker is? Basically, I have given 3 points, if you see, and the marker basically marks those 3 points. So all of this is just a graph connecting it. Where does it actually know what the values are for this graph is where the markers are. So I've given marker equal to 8, marker size equal to 15 pixels across, and marker edge color. It's not very visible here, but if I zoom in very closely, you'll notice there's a yellow tinge at the end. So that is where marker edge color comes into play. Line style, this also matters. So here, if you notice, line style I've given passed in a string that is dash and dot, which if you notice corresponds to dash and dot. And there are other variables that are also available. Now, if I just put a single dash, you will get a straight solid line. If I put a double dash, you'll get a dashed line. And let's just revert back to the position we were in. So yeah, this is your most fundamental. Does anybody have a doubt? Okay, cool. Now this is the most.
Can you please explain the first argument of this plot function?
This.
Yes, this one.
Yeah, this is your x values and y values. So x and y as a parameter, you'll pass it. Now, ideally, you could do it like this. So I can do x equal to 1, 2, 3, and I could do y equal to 4, 5, 6, right? And I can just replace these as x and y. If that helps with comprehension, then I can do that as well. This Matplotlib is looking for a list of values of x and the corresponding list of values of y. And you would want them to be the same size. If you're passing in 3 values for x, you would want 3 values for y. Otherwise, it'll throw up an error. So yeah, it's just looking for values to correspond. So if it starts, it will start reading here. It'll look at 1, 2, 3, and then it'll look at 4, 5, 6. So it will correspond 1 to 4, which is what you're seeing here. It will say 2 to 5, and then it will be seeing 3 to 6.
Okay,
actually, is that understood? That is the list. X and y lists. You want to pass a single dimension list for x and a corresponding size of a single dimension list for y, and Matplotlib will correspond the values. So the first element of the x value, first element of the y value will correspond together to make 1 point. And then it will try and plot these points through a straight line. So if you want a curved line, then you would want multiple points because it will just put a straight line between the 2 points. So if you want something like x square, you would ideally want to pass a lot of values so that your curve looks smooth. Is that understandable?
Yes.
Wonderful. So, and yeah, plt.show is basically in
Anirudh.
this. Yeah.
Just a minute, there is one doubt. So Jaydeep, go ahead.
So what I want to ask is, in the picture there is the point interval is 0.25. So is it like is it 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 is inserted into the code, or just
Yeah.
the Python figures it out itself?
Yeah, I get what you mean. See, the thing is, if you don't pass anything, Matplotlib will default to a default resolution. So if you notice throughout the thing, when I don't pass in a particular resolution, it will fix itself to this default resolution. And then it will fix itself to a default number of ticks. They call this ticks. And if you go down here, 1 second, I would pass in x ticks and y ticks. So in this case, if you notice, if I do 0 to 5, it restricts itself to only 0 to 5. But in this case, I have not given any values. I've let it do its default. So in this case, it has figured that for my resolution, which I set for myself, this would be the most aesthetic part, which will also cover all the values. So it needs to cover 1, 2, and 3. And so it needs to give in equidistant values for the resolution which it has chosen for itself. So that is why you're seeing a 0.25 interval. This will change automatically unless you force it to show only a certain amount of values. Was that an answer to your question?
Yes. Thanks.
Okay, cool. So now let's move on to 1, 2, 2, 4, 3, 6. Once again, all of this will be available at the end of the session. So I would advise you to not go through all of this line by line. These are just syntaxes. What matters is how powerful this tool is, right? So just know that you can change line style, marker edge color, marker size, marker. These commands are just on the fly. You can even perhaps Google it if you're working with it. So these are all just syntaxes. That matters less than knowing what this library can achieve, which is what I want you guys to take home from this session. But what all this can achieve. So as I was saying, this is actually a very powerful library, and just look at the intensity of the markers. So I showed you an octagon for which I passed a string 8. Now you have a square, you have a pentagon, you have a plus, a filled plus, a star, a hexagon, 2 hexagons. I mean, you can see for yourself. These are all just the markers alone. Such is the level of customization that's available, and this library is free. So like, it's very amazing what this library can offer, and it's actually pretty well done as well. Anyways, now I would also want to introduce a shorthand notation from the previous line to this line. All I've done is do 2 things actually. One, I've introduced a shorthand notation, and I've introduced plt.legend. If you notice here, I labeled my graph as label. Where is it? Label it as x plus 3. But if you notice the graph, there is x plus 3 is nowhere to be seen. So where does that x plus 3 go? The x plus 3 goes into the legend. So here I've come up with a different graph that gives me y equal to 2x. So I've labeled the graph as 2x. If for some reason I want to label it as 2 into x, just for you to show, you can see that now it replaces itself into 2 into x. Why is that? Because the label function is just to label it in the legend. In this case, we have only one graph. But if you're doing multiple graphs within the same canvas, which is what we'll be seeing next, this legend is very useful. That is why it's important to label your graphs. Moreover, before the label, you can pass a shorthand notation like this, which is color marker line. So here I put color as R, which is shorthand for red. Marker, I put a full stop, which is a shorthand for the dot marker. And I put a double dash, which is, as you covered before, a shorthand for double dashed lines. So let us say I make this a single dash. You will get a solid line. Of course, you can still add the customization options, such as, I will just go through this pretty quickly. I can just add marker fill color equal to blue, which you can give it as blue as well. Let's not go into the shorthands right now. Okay, it's very less visible, but if I zoom in, you can see a tinge of blue here. I'll have to change the marker size for that. So you are still allowed to play with the customization option, but if you want to save some time, you can just quickly give marker, color, and line style, which is what you will mostly be playing around with. All of this is just final touches, which you can spend more time. But if you want to see something very quickly, you can pass the shorthand notation. Just quickly remember it's color, marker, and line, and you'd want to put it before label. That's the main thing. And as we saw, this is plt.legend. The nice thing about plt.legend is this is automatic. So if you have a graph that goes like this for some reason, then this will come here. So the library will take care of that for you. Now, what we will do is we'll go into further customization option. As I said, Matplotlib is mostly a data visualization library. So it offers plenty of customization options. So if you notice here, the only piece of data that you can infer from this is a y equal to 2x graph. That too because I put it here. This graph is not really well labeled if you ask me, because there's just a random values in x-axis, random values in y-axis. So but you can add so much more data within the same by just adding a few labels. So now let us look at how much we can customize this graph. We'll start with plt.xlabel. These are pretty self-explanatory, so you can go with x label is x, y label as y. If I come here, you can see you have x and y. And then you're putting plt.title and giving it name as single graph. And then you can pass in a dictionary called font dict. So this will give a font name and a font size. There are other customization options, but I think for the purposes of this, the main things you'll want to be looking at is font names and font size. So here, we have set font size as 20. I'll set it as 30 for the time being. And if I do it again, you should see a bigger single graph. And yeah, notice this is because Collab, you'll have to upload every font by yourself. If you have worked with Collab before, you would know that you would need to upload everything one by one by yourself. So that is why you're seeing this font family is not available. Furthermore, what we can do is, one second, font defaults to 1. And as Jaideep asked me before, if you're not satisfied with the automatic ones which are being given by Matplotlib, you can always set your own ticks, which is 0 to 5 I've given here and 0 to 10. So that should give you everything. If I want to add something in the middle, let us say, like I want to add 9, it will automatically adjust its thing to give 9. In this case, notice that I'm passing in integer values directly. So Matplotlib is able to directly give them 0, 1, 2, 3, 4, 5, because it's able to correspond to the integer values of the graph. Now, what if I pass strings? Like I can also label them as a large dash, right? I can give them 0x1 or 0x2 for some other reason as will come in the future. But for that also, Xtrix can handle that. I'll show you how in a bit of time. But for now, understand that you can pass in integers or you can pass in strings. If you pass in strings, you'll also have to pass in where those strings go. I'll explain how we can do that in a bit, but just know this. From this, we have done this before. We are giving in X values, we're giving in Y, and then we're plotting in everything using a label. One second. Yes, so all of this we have done, and I'm labeling it to X, and then it's coming as a legend. Now what I will do is I'll plot second line in the same graph canvas. So yeah, this is what I was saying before. Until now, we are looking at a single graph. So that is, it's fine. So if you notice, I don't necessarily need to give it a legend because it's a single graph. But as I said, this is a canvas, which means you can plot multiple graphs in the same canvas. So how can you do that? I'll show you how you guys can do it right now. So now, first thing you can do is, again, I'm giving a plt.x label, plt.y label, setting the labeling, and then I'm putting a title single, actually I'll name it dual graph. Dual graph, same thing, collab doesn't contain the false, so it defaults to 1. And then I'm giving the plot, putting x comma y. Now this is where the second part comes in. Until here, we have done already in the previous. I have pretty much just lifted it up and put it here. What is new for this is, if you notice, I'm putting np.arrange. So what this command does is, I can show it to you guys right now. What this command does is, it will take values from 0 up till 12, not 12 included. This is exclusive. I think I even covered this last time. In NumPy or Pandas, if you're giving a final value, that final value is usually excluded. So it will give you a range from 0 to 12 minus 1 in a spaces of 2. So in this case, it'll give you 0 to 10. I'm going to print x1 and show you. It will give you an array of 0 to 10. 0, 2, 4, 6, 8, 10. So you can use np.square, which is a command which will just square all the elements of an array instead of you doing it iteratively. And then now, this is some list slicing which I want you guys to know right now. This is probably some useful syntax, so probably go through this or like observe this right now, which is this list slicing, which basically says start at where you start, end at where you end, but skip one value in the middle. So every other value will be chosen. So if I am to print out xtick, one second. Here, you should see that it will skip every value. 0, 2, 4, 6, 8, it will just print 0, 4, 8. Because in this case, xtick is 1 second. X1 list to 0. Yeah. As you can see, it's skipping every other value. And since there is nothing on 12, it will only take 0, 4, and 8. And ytick will do something very similar. If you want to see, y1 will just be 0, 0, 4, 16, 36, like that. It will just square every command. And then now you notice I'm using the same plt.plot. Right. So notice here, I'm using the same plt.plot and I'm labeling it as x square and I'm giving a marker edge color as blue and a marker fill color as red. And now I'll show you my final plot, which I have gotten. Notice, like I have plotted two graphs in the same, how do I put it? I plotted two graphs in the same canvas, which is actually very useful if you're trying to do comparison charts, right? And another thing, if you notice an artifacting here is that, as I said, what Matplotlib will do is it'll take 2 points and draw a straight line without thinking much. So although this is curving up, you can see actually these two lines coincide. While it tries to find the second point of x square, it's actually just following a straight line, which is along y equal to 2x, which is pretty interesting. So which is why it's always good to have more data points so that you have a smoother looking curve. But yeah, that is where we stand with this. And as you see, once again, since I have passed in the xtick and ytick values by myself, it is not defaulting to anything. And this looks neater, if you ask me, because I'm not doing 1, 2, 1, 3, 5, 7. It looks that much more neater and you have gotten what the graph is trying to tell you. Another thing that I want to add is, if you see X label and Y label, even this can take in a font tick. Wait, I'll show it to you right now. I can just copy this exact same thing and I can put it here. Notice how X has grown in size. So yes, even X label, Y label, and title can take in the same font dictionary, right? So that is where we are. Oh yeah, and then I also wanted to find a small error in this code. Can someone find it? There is an error. It is, you can see it's a semantic error.
So the plt.legend should come below that plt.plot.
Wonderful, yes. Because this is a function in itself, right? And when this function runs, no handles with labels found to put in this legend. So this, I think it's pretty easy to make this error. At least I made it once while I was like working with this. So it is pretty easy to make this error. And so ensure that you have labeled everything before you run this function, which will basically print that out into the final graph canvas. So that's great. That's great that we have interaction. So yeah, anyways, we have X and Y axis. Notice, and so now what I will do is I will first upload a CSV file. I had it right here. Give 1 second. It looks okay. 1 second. I'll quickly upload the CSV file and then reshare the screen. The runtime got disconnected while we were waiting. Yeah, we're back. Sorry for that. The runtime got disconnected. Anyways, so we have a CSV file in our thing which I have taken as petrol.csv. Now this is a much bigger CSV compared to our the serial that we were looking on Wednesday. See how much more time it takes to load. And see, there are some 505 pages. So you can think about it, the 10 per page. So there are like 5,550 rows. And so if you had noticed at the end of NumPy in the documentation, not NumPy, pandas, I had uploaded the part which actually it will allow you to read data chunk by chunk, which is something that I didn't have time to cover last session. But you would want to understand that when I run data sets that contain, this is just, I mean, I'm saying just 5,000, but there are some data sets that contain hundreds of thousands of rows. And so even if you have like 8 gigabytes of RAM, it's not going to be enough to handle that much data. So what Pandas allows you to do is, I'm not using it here because I'm splitting the data sets anyways, but Pandas allows you to read these data sets chunk by chunk. So you can choose a chunk size. I will cover through it if I have time, but most likely you can go back and check the notebook that I used. It will allow you to add chunk by chunk so that your RAM doesn't get overloaded and you don't bog down your computer. So anyways, yeah, you can see that this is much more substantial compared to the serial, which just had 77 rows, if I remember correctly. This has 5,050. Anyways, this, if you had paid it, I mean, if you had been part of my session last time, I have gone through all of this, what this means for the sake of revision. I'll go through it again. pd.readcsv. It's basically reading content. That's the path name that Collab has given me. And then I'm locating. I'm going into the data frame, which is what I'm calling this array that I've gotten. I'm going into that data frame and I'm locating the column city. And what rows do I want from the column city? I want the rows which are attributed to Chennai. So making a data frame that only looks at the petrol prices in Chennai. And then I'm also resetting the indexes so that it's a bit easier to work with. Right. Is everything understood till now? Actually, I have to pause myself. Does anybody have any doubts apart from the ones that have been put in the chat or been asked to me? Very good. Okay, fine. So what we are looking at is DFC. So I'm naming Chennai's data frame as DFC. So now again, if you notice, xtick, ytick, and I'm taking dfc.date array from 0 to the end, but I'm taking only one element out of 100 elements. So using list slicing to only take out certain marks. Even this, I will show you, will not be enough. So this is another indexing method that you can use. So notice that I've done DFC of date, no? It is as good as writing DFC.date. Keep that in mind. It's a bit of a shorthand notation, but it helps you from writing this down, this squared brackets, the single quote stuff that you will not be usually using in a keyboard. So this will just speed up your process that much. But these two are pretty much the same. They'll return an array which contains all the columns of the date column. It'll return the column of the date from the data frame of Chennai. So look at how much we are taking our index. I mean, how much we are taking an array. So what we had a particular data set out of which we pulled out Chennai, and then out of that we are pulling out only date and rate. So that is I mean, it's kind of showing you the very basics of data analysis, right? This is some 5,000 rows. This will have some 1,000 rows because it's for five cities. And then we're pulling out only these two. Suddenly your memory size would have decreased by a lot. So anyway, that is why I'm not using a chunk size in this case, because this cloud can handle around 1,000 rows at a time. That's fine. Anyways, we are having tick values. So this is important. Last time, if you remember, just a couple of minutes ago, I mentioned that if I am putting ticks as integers directly, then Matplotlib library will have no issues directly putting them. If you notice back here, I have given the ticks directly as integers. When I'm passing them as integers, it will know 0 goes at the origin or slightly from the origin. And then it will know 10 is farther away. Like it knows where to relatively position them. Whereas if you're looking at wait, I'll show you the CSV. I think it will make so much more sense. If you look at the dates, which is what I want to do, this is not a integer in the classic sense, right? How will Matplotlib library knows that 2012 401 was ahead of 2012 629? Like, I mean, opposite. 29th June is ahead of 1st of April. It doesn't know that. It's not that advanced. So in that case, what you will have to do is you'll have to give Matplotlib library a tick values parameter. So if you notice, before I was only giving xtick, but in this case, I'm giving xtick as well as tick values. Why? Because this is essentially a string. This has been stored as a string. So Matplotlib library doesn't know where to read the string from. So what it does is it asks us for an extra parameter where it knows where to insert these strings. So it knows that there are 11 elements, 11 strings, but those 11s can also be from 1 to 11, or they can give you from 100 to 1100. So this tick values will teach Matplotlib that put the first element at the 100th point, put the second element at the 200th point. So as I said, this has around 1000 elements. So I mean 1000 elements or around 1100. So I put 1100 as a kind of final element thing. So now I've done PLT.ytick. Why ytick? Because ytick is a rate. It's a direct integer. So it will be able to handle that. I've also showed you the rates to show that it's an integer. You don't see quotes outside of them. So once again, I'm putting x label as dates, y label as rates, and I'm putting x ticks as tick values, and then y ticks as just ytick because you're passing an integer. Once again, we meet our role command, plt.plot, pass an x array, pass an y array, and then you have r signifying red. I have not put any markers here because there are more than 1000. When I put markers, it turned out to be very bad. And then label, I'm giving it as Chennai. In this case, I'm not using a label, but still. And then I'm showing the final graph, which if you see here is a bit of a mess. Like until now, we were looking at pretty simple data types with like more than 4 or 5 markers, right? But in this case, look at this. I think for an initial doubt, I did say that the Matplotlib library tries to default to an initial resolution, which it does not change. If you notice, all of these resolutions have been the exact same throughout the entire session till now. But for data as big as this, that's just not going to cut it. You have so much grouping here, something that is just overwriting. This is not and even the graph, if you notice, it's not really that good. It's pretty low quality. So we can deal with this either by making the font size small or the canvas bigger. What I'm going to do in this case is going to teach you how you can make the canvas bigger. So again, I'm going to introduce one extra command, which is plt.fixsize. This is your new resizing command. And in typical fashion, all of these are in inches. So this is going to be 30 inches by 30 inches with a pixel density of 300. All of these I've just lifted it and put it back from the previous. Just your focus should be only on this. So once again, PLT is a library of functions. We are going into the figure function of the PLT library. And then we are choosing the fixed size parameter. How big do you want your canvas to be? And I'm choosing it to be 30 inches by 30 inches. And I'm giving it a pixel density of 300. So for every inch, it will try to put 300 pixels within that inch. So for that inch square, actually. So 300 pixels per inch. With this, your new resizing command, rest are all previous commands. So I'll run this right now. It will take a bit more time if you notice, because it's pushing larger pixels.
Maybe I do till now. Do you want to answer this question on the chat? What is the role of
100%.
text values in xtick command?
Yeah, 100%. Yeah. I'm not able to see the chat, so either
Right.
someone
Yeah,
can
I'll
help
read it
me
out. What is the role
100%,
of tick values in xtick command?
So as I mentioned, I will pull this out and then I will. 1 second. I'll pull this entire thing out. So see, I have given a set of integer values here, right? So if you notice, tick values is an integer array. It has a data type of integer. And if you notice xtick, I'll go back to the CSV. If you notice xtick, this cannot be shown as an integer. No matter how I iterate, dashes cannot work on integers. So, but we want dates to be as our x-axis because again, what are we trying to achieve with graphing this? We are trying to see how the petrol prices are trending with the days of the years, right? So this, your x-axis should be your dates and your y-axis should be the rates. Y-axis, no issues. These are float types. These can handle everything. The Matplotlib library can understand relatively that 75.8 is greater than 74.9 and place that higher. Although in this mess, you cannot see it, it has placed it higher. But this is a piece of string and you cannot relatively position two places of string, right? So if I have 2020, 08, 19, it doesn't know that 2020 of 08, 20 is going to be one step greater. It'll just get confused. So if you just try and pass xticks, which is, so xtick I have put later, this is a string. So it'll basically just throw an error. It's like I don't know where to put all of this. You have given me 10 random values. Where do I put it here? It's not going to equidistantly space. It won't do that. It's not just going to equidistantly space all these 10 and put them. So to deal with that, you have to pass tick values. So basically what it tells is, here, tick values is this. It will pass an integer array. So what it will do is, it will tell xticks function that for the first element of the string, so if let us say that was 201208 something, right? For the first string, that will go in the 100th marker. Okay, so that will go in the 100th marker. So which means it will start from 0. It will find the 100th point where the marking was made, and then it will take that particular string. So it will take this particular string and drop it here, which was 2002 in this case. And similarly, if you take the second value of the string, which can be something, put 100 days after that. So some like 2000, if it's 2002, let's just put 2003 for some random day on 2003. If this is your second string, then that it will move another 100 elements, because I put the second one as 200. So it will move another 100 elements, and it will put this particular string as a tick over here. So that is the function of tick values in xticks and yticks. It allows Matplotlib library to understand strings in a more relativistic manner rather than just a piece of string, which you cannot say whether they're greater than or less than. Is that clear? Ashish, is that clear? Was there any chat?
Yeah. So he understood that. Yes. So cool.
Wonderful.
Just like move on a little bit faster. No, we are kind of
Understood. Yeah. I think we're in our final bit. So yeah, finally here, if you notice, we're coming back to the 30 inches by 30 inches with DPI of 300. It took us around 10 seconds to execute this, but this is just much better, don't you think? There is still a bit of artifacting, but we cannot help that. We'd have to go for a much bigger canvas size. But just look at this. All of this is just much better, and the graphs are much easier to analyze. All the nuances is easily understandable. So if you're trying to do any real world analysis, such a big canvas will definitely help you out to understand what each data is and everything. Now, finally, I like to almost conclude with this, which is using the subplot command. So this is just Chennai, but this dataset contains Hyderabad, Delhi, Mumbai, and Bangalore. So what I've done is I'm going to teach you how to use subplots, which is also pretty useful. Subplots is basically splitting the canvas into 4 smaller canvases. So here I made the use of this entire canvas, but I'm just going to teach you how to use 4 smaller canvases here. So again, I'm like I did in the previous session, I'm creating 4 separate data sets for Hyderabad, Mumbai, Bangalore, and Delhi. And then I'm doing this exact same process that I did in the previous thing, except I'm repeating them for Hyderabad, Mumbai, and Bangalore. And what I'm doing, I'm giving you the same tick values, but this is the main thing. I'm giving plt.subplot. So now this is a very important syntax. I'll just spend 1 or 2 minutes on this. See, plt.subplot. Subplot tells the Matplot library that you need to subplot tells Matplot library that you need to convert your one big canvas into X number of small canvases. What is X? Which is where you pass this numbers. So what is 2, 2, 1? This is very important. 2 is the number of total rows, and 2 is the number of total columns. So if I put 2 cross 3, which I don't need right now, I'm plotting only 4 graphs. But if I do 2 cross 3, then it will say 2 rows and 3 columns. So you'll have a 2 by 3. So here we're having 2, 2, so that will have 2 rows and 2 columns. And this is the first graph. So that's where 1 comes. I'm labeling it as Chennai, and I'm plotting it. Similarly, 2 by 2 matrix. The second part will be taken up by Hyderabad. The third part will be taken up by Mumbai, and the fourth part will be taken up by Delhi. So if I'm doing the, okay, 1 second. I executed the wrong graph. Here we go. 1 second. It's still executing. Since it's a larger graph, it will take some time. So because in this case, see, there are 1,100 rows per city, and I'm doing it for 4 cities. So it has to pass through 4,000 rows before it can give me a valuable graph. So see, it's going on for 19 seconds. And once it presents itself, you'll realize that they'll be seeing a grid. Give it a couple of seconds. It's a pretty big graph. And I didn't even resize it. So this is at the default resolution. So imagine what the situation will be if it was a larger than, like I did a 30 by 30 inch for this. It would definitely, I found it very difficult. So while that's executing, I'll just quickly go to, okay, there we go, it's back. Okay, did it in a 30 by 30, fine. So here you can see we have 4 graphs, and I've labeled it Chennai, Hyderabad, Mumbai, and Delhi. As you can see, it has given equal spaces, and it has graphed all of them. You can also combine all of them under one canvas, but this particular data set has recorded different values at different days. So the graph is not right. You'll have to do some sorting. So for this current sake of simplicity, I'm just going to go with this. And if you notice, there has been a drop on one particular time, but this drop has been in various leveling of magnitude. So yeah, that is that. If you're still not convinced with the syntaxes, you can always go through the collab. And since we're running short of time, I'll quickly skim through bar graphs. It's actually pretty simple. We're going with x-axis, once again, labeling, y-axis, integers. And in this case, you don't need to worry about the tick values because these are 4 independent entities. So you can directly give them strings. So I'm giving A, B, C, D, 1, 2, 3, 4. And I'm showing the x bar. This is the key difference. I'm putting plt.bar. Before it was plt.plot, now it's plt.bar, and you're having a very simple value. You can put tick values even here, but for what y-axis, the story is a bit more different, as in you can pass in integer values. If you use bar h instead of bar, you'll have horizontal values. It's as simple as that. And in this case, I've also showed how you can customize it. So you can do set underscore hatch. So if you're giving bar hatch to a variable, you can use set underscore hatch to find various patterns. This is a simple customization option. Just know that you can customize the bar. And finally, I just want to show a simple this thing. There is no difference in this at all. It's just to show how bar graphs are used. So what I've done, I've put comparing 4 fuel prices on the same day. So yeah, you can see there's a subtle difference. You can subtract a common number to get a more nuanced view of the graph. So since it's like only 1 or 2 rupee difference in the scale of 0 to 70, you can see there's only a little bit of a difference. But you can also scale the graph down by subtracting a common value so that you can you can have a much more better view. That's it. And it's also giving you a date, which I have done on the top. So yeah, that's been it for this. If you have any doubts, you can ask me. There are also further references, namely Seaborn, which you can go through. But this is all you would need to do your first, to at least help you with your first task and also get a better overview of Matplotlib library. Any doubts?
Is it possible to plot 3D?
It's a good question. As far as I know, that would require that will not be possible in the 2 kinds of plots that I have covered for today. But as far as I know, 3D plotting is not possible.
Okay.
But yeah, I am not 100% sure about
Actually,
that.
you cannot plot it like this. You can create an interactive environment to like show 3D plots. You can actually do that.
Okay, like a spectrum, like a bell shape.
Yeah,
if
it
you
is.
want to.
It is not available in PyPlot, but it is available in Matplotlib. So
Okay,
the
okay,
PyPlot library doesn't have 3D plotting. So
Thank
I mean,
you,
you can check out the Matplotlib documentation to know more about that, I guess.
Yes, thank you. Yeah, your presentation was very clear. Is good. Thank you.
Thank you. Thank you so much. Once again, yeah, everything will be available. So you can go and check it out yourself in the GitHub repository. Thank you, guys.
Okay, thanks, Anirudh. So just before we move on, I thought it'll be a good time to introduce what the task is for this week. So if you go to the GitHub repository, which is available on the description in both the WhatsApp groups, you can find out this folder called task 1. So there is like a brief description of what the task is. And basically inside the data folder, you can find a CSV file. So it is similar to what we had used in this petrol data set. So there are some columns, and the description of each column is mentioned in the README file. You can go through it. So basically, the task is to create interesting visualizations of this data set and find insights from whatever you can visualize. So you can make how many ever visual insights you want to create, and then basically it's to understand the data through visual representations and not through any machine learning model. So this is a good way to start with feature representation, and we actually will cover this in the later sessions. So we use visual representations to actually cover to actually find out which features are more prominent and which are more insignificant. So so basically we thought it will be the ideal task one. So you can find out the task one on the GitHub repository, which is linked on the group's description. So once you are done with how many ever visual insights you could come up with, you can upload your Jupyter notebook or whichever script you use. You can upload it to this form. So the deadline that we had set for this is on July 11th, that is Monday, just before the session 3 starts. So if you have any doubts, feel free to post it on the groups, and I guess all the best for the session, all the best for the task. Yeah. Okay. I guess we can move on. Srikar, please continue.
Yeah, sure. I hope you can see my screen. Let's start with the introduction to ML. Now, this is the main part. This is the interesting part. Until now, you have learned the basics. From the basics, we'll move on to what actually machine learning is. Machine learning is a subfield of artificial intelligence, which revolves around the concept of teaching a machine. Basically, the machine is trying to imitate the human brain. You are giving the ability to learn. You're providing it to the machine. Machine learning is a very vast and rapidly expanding topic. It is being continually partitioned and subcategorized based on how and where it is used. What machine learning does is it offers a better way to solve problems and answer complex questions. That is why we come up with this concept, machine learning. What exactly we are doing in machine learning is we are training a piece of software. Now, this software is known as an algorithm or a model. We use the term model more commonly to make predictions from past data, basically. Let's take an example. Let's say you have preferences in your songs. Let's say I have data of your song preferences. I know that you like fast and very intense music, and you dislike light and very relaxed music. Initially, I'll create some model. We'll see how to create this model and how model is working later on. But what exactly this model is doing is it will take in your past data or previous liked songs. It will analyze for similarities. It will analyze for what you like, what features to take in account. And when you pass in a new song through this model will tell me, okay, you like this song or you won't like this song. It is basically predicting something which is based on previous data. This is the basic concept of a machine learning model. It's pretty simple. There should be no doubts here. Before we move on to types of machine learning, we'll talk about. Yeah, sorry.
Yeah, I think it'll be better if you share the Colab notebook on the groups.
Yeah, sure. Once again, I'll put it in the chat. Give me a second. Yeah, it's there. I've put it up. Let's move on. Applications of machine learning. Machine learning is used in various fields of study and research. It is very flexible and volatile. So let's say recommendation system on your Facebook, Instagram, speech recognition, Google and Siri, image recognition, satellite recognition, medical diagnosis, stock market trading, spam detection, fraud detection, self-driving cars. All of these use machine learning algorithms as their base. How and why it's being done is pretty clear, but how it's being done is very complex. Let's break it up and understand how. How it is. There's basically 3 major branches in this machine learning, which is supervised learning, unsupervised learning, and reinforcement learning. We'll go in depth into supervised learning in this session. Unsupervised learning will be briefly touched upon, and same as with reinforcement learning. Let's start off. What is supervised learning? Supervised learning is a type of machine learning where we deal with labeled data. What do I mean by labeled data? Now, you must have, it's pretty self-explanatory that what training data is to a model. Basically, this model will take in some prior data, which is called the training data, to analyze, to give new predictions. What I'm saying here is this prior training data is already labeled. That means their ground truth values are already known. When I pass in this new data, this model will predict something and it will validate against already present data. Let's take an example. Let's say you have a basket of fruits. One by one, I pick out fruits. This basket has, let's say, apples and bananas. If I pick out a fruit, my model will predict something, but I know that this particular fruit I've picked up, let's say it's an apple, and my model says it's a banana. I'll go and tell the model that no, you've done something wrong. This is not a banana. This is an apple. Change your perception. It'll change its perception. And based on this, the model will try to learn that, okay, anything which is round and circular in shape, it is an apple. Anything which is greenish, yellow and curved, this is a banana. This is how it will try to figure it out. This is how supervised learning works. And this similar example can be done in an unsupervised manner where unlabeled data is also where we can work with unlabeled data, which Varsha will explain in a bit. Under supervised learning, we have two major categories, which is classification and regression. Under regression, in this session, we'll be going deep into linear and polynomial regressions. Under classification, we'll go into logistic regression. That we'll see in a bit. We'll dive into unsupervised learning and reinforcement learning right now. Varsha can take it from here.
Yeah, I believe you guys can see my shared screen. Right. So I think we'll get started with unsupervised learning. So what is unsupervised learning? Unsupervised learning is basically you're given unlabeled data or not classified data where you use the AI algorithm to identify patterns in it, basically. So if I explain with an example, as Shekhar mentioned, in supervised, you'll have labeled data. That is, you'll know what is an apple, how it looks like, and what is a banana and how it looks like. But in unsupervised learning, you will be given a basket of fruits. Suppose you don't know which fruit is what, so you don't know what a banana looks like and an apple looks like. So how it is trained is that it searches or looks out for commonalities or similarities in it and groups them into certain smaller classified groups. So basically, you won't know which is what, but looking upon starting with the similarities, you will be grouping it, right? So it's similar to a human, how a human learns, right? So that is what is the unsupervised learning means. And there are quite a few disadvantages in unsupervised learning because it is intrinsically more difficult than supervised learning as it does not have a corresponding output, and it also might be a less accurate compared to supervised. And now there are further classifications under unsupervised learning, that is clustering and association. So let's see what clustering means. So clustering is a method of grouping the objects into clusters that objects with most similarities remain into a group, and the ones that are having lesser similarities will remain in different groups. So you can see there are groups formed based on the commonalities or similarities that the model identifies. So that is what clustering means. And coming to what association is. So association is finding the relationship between variables in larger database, right? So it determines the set of items that occur together in the data set. So let's go with an example. So suppose if you order or buy something online, you will also see a few suggestions popping up saying that the customer that bought the same product also bought corresponding other products too. So it will give you a suggestion. So that is what association does. So what it does is it will go through the data and it will come up with a larger data set which were seen similar, like, or which was grouped into a similar classification. So that is what association basically means. Now, moving on to reinforcement learning. So let's see what reinforcement learning means. So reinforcement learning is basically system interacts with a dynamic environment in which it must perform a certain goal. Okay, you'll have agent and environment, and it must perform a certain goal. The system is provided with feedbacks in terms of rewards and punishments as it navigates its problem, right? So basically, if you take a right step, there'll be a lot of pathways if you to perform a goal, right? So based on the pathway taken by the training model, it gives you it if you take a right step, it will give you a reward. If not, it will be the model will be punished. So at the end, the pathway that follows that has the highest reward will be chosen. So what is the input here? The input here should be an initial state from which the model will start, and the output here are many. There are many possible outputs as there are variety of solutions to a particular problem, right? And the training data will be based upon the input. The model, it will actually return to a state and the user will decide a reward or punish model based on its output. Okay, so the model is continuously learning at every step here. So the best solution is decided based on the maximum reward. So let's see where and all reinforcement learning is applied. So you will see its applications in obviously industrial automation, machine learning, data processing, and yeah, it is also I'm pretty sure a few of you might know about a Chinese game, Chinese abstract strategy board game, which is called Go. So there was a software computer program developed called as AlphaGo, which basically defeated one of the world champions of Go game. So you know that how powerful reinforcement learning can be, right? So okay, so that is it for RL, and now let's start over with regression, which is, as Shekhar mentioned, it is under supervised learning. It what regression basically does is it finds a relation between dependent and independent variables. It's also used as a predictive model in machine learning. It's an algorithm which is used to predict continuous outcomes. Right, that is what regression does. So I think it's pretty clear till now. If anybody has any doubts, we'll get started with linear regression, but till now I think it's clear. If you have any doubts, you can drop it in the chat or ask. Okay, so okay, let's start with linear regression. So yeah, under regression, we'll be mainly talking about linear regression and polynomial regression. So let's get started with linear regression. Here, as you can see, there's a linear equation written here. I'll tell you what each, yeah.
There are a couple of doubts. So we just maybe if you could look at the chart, that'll be great. Can answer them.
Yeah, I think I can see a doubt. Yes, RL works on reward and punishment basis. So basically, the pathway taken, the one with the highest reward is chosen as the best outcome. So I think that is what you're intending to ask. So that is what RL does. And okay, I think you want to know what regression is again. Okay, I'll try telling what regression is. So basically, regression is trying to find a relationship between the dependent and the independent variables. I'll be telling what is dependent and independent variables when I get started with linear regression. So it is basically a predictive model, modeling in ML. It predicts the outcome, right? So by undergoing multiple process or modeling or training, you call it training. So by undergoing training, it will predict the possible outcomes. So let's start with linear regression. So linear regression is, as you can see the equation here, so y here is the dependent variable or the prediction. So y is the dependent variable, and as you can see here, x1, x2 up to xn, these are called the independent variables, which can be also called as the explanatory variables. And you can see certain coefficients mentioned here, beta 1, beta 2, up to beta n and k. So betas and k's are called the parameters. So basically, you train the model to get the best possible, best optimized or best optimized parameter. So let's see what each one means. And yeah, so you optimize. So linear regression attempts to model the relationship between two variables by fitting a linear equation to observed data. So here, let's have a simpler equation, a linear equation, y is equals to mx plus c, where c will be the intercept and m will be the slope in normal language. If you say it's m is a slope, or it's also a parameter which you'll be finding out. You'll be seeing how you find out m. So yeah, let's start with so basically to optimize the values of parameters such that the error in prediction is minimized. You come up with a function called cost function, which basically will be the minimum of the root mean squared error of the model. This equation here is basically the root mean squared error of the, we'll be finding the root mean squared error of the model. So it is obtained by subtracting the predicted value. This h theta of xi is the predicted value from the actual values. The cost function will be the minimum of these error values. So I'll tell you why. Okay, so if you look at the equation, j of theta naught comma theta 1 is equals to 1 by 2m of the summation. So what is this 1 by 2? This 1 by 2 is basically, it's you will come to know why there's 1 by 2 later on, but it's basically the mean. So you'll be having this equation, this function, to find the minimum error in the predicted model. So predicted parameters. So here, when you plot the graph, you'll be finding the graph to bar contour curve, and this is how it looks like. Here you have theta 1 and theta naught on the x and y axis, and j, that is the cost function in the on the z axis. So this is how the graph looks like. And so moving on, I think I didn't mention what theta 1, theta naught is. So basically, as we have seen before, theta 1 will be the intercept, that is c here, and theta naught will be the coefficient of x. Okay, so now moving ahead, right? So once we find the best theta 1 and theta naught values, we get the best fit line, so that with minimum error. So it will be covering most of the data points in the data set. So to do that, you'll be using a function called, an algorithm called gradient descent, which is used to optimize the cost function or the error of the model, right? So it is used to find the minimum value of error possible in your model. So the error in your model can be different at different points. So this is, suppose this is an example. So you can see there are different points. This the cross represents a point on the model, on the cost function. So if you think, so basically, if you in the gradient descent, you find the error in your model for different values of input variables. So this is repeated, and soon you can see the error values keep getting smaller and smaller. So how we'll be seeing the equation here. There is a derivation and equation here. I'll be explaining how it works basically. So what happens here is you can see that there are two steps. So we'll call them a step. So suppose I start from here, right? And I move from one point to another point, and based on the this equation. So I will be explaining how it works. Now, in this equation, as you can see here, theta j is equals to theta j minus of alpha of differentiation of cost function. So what is alpha here? Alpha is basically it's called a learning parameter, which is actually a hyperparameter. And what is its actual? What does it do? What is its use? Is that it basically decides how fast you can move down the slope. So this is the minima or where you have to reach. It's a minimum point where you can get the least possible error. So you'll have to move from here to here. So alpha decides in which direction or how you reach this point, right? So how and obviously you will have to be careful with the alpha. If alpha is too small, then the error, the process of finding the minimum error will become too cumbersome as you'll be moving slowly. And if alpha is too huge, the steps taken might be big enough that there's a possibility of missing out on the minimum point here, right? So you'll have to be careful with taking the value of alpha, which you'll be finding out later how you find that. So basically you'll be finding the alpha here, and yeah, so this is the equation. And if we differentiate, if we differentiate the cost function, this is what happens. So why we took 1 by 2 previously is that it simply gets cancelled, and it'll look a simpler equation. You get a simpler equation without any coefficient. So you'll take a 1 by 2 and it becomes simpler equation, and you'll be repeating this again and again until you arrive at the you'll not exactly arrive at the minimum position, but you'll be close enough to the minimum point in the cost function. So that will actually give you the minimum error. So basically that is what it means. So as I mentioned, theta naught will be this theta naught will be the intercept, and theta 1 will be the coefficient of x, which we have taken. So this is how linear regression mainly basically works, but things get more clear once you see the implementation part of linear regression. And I think this part Shrikar will continue. So I think, yeah, Shrikar can continue from here.
Yeah. Yes. Hang in there for another 10 to 20 minutes. After that, you guys will get a 5-minute break. Then we'll move on to polynomial and regression, polynomial and logistic regression after that. See, the main crux of this linear regression part is these two equations. Up until now, we have learned the theory. The theory is important. Yeah, that is all true. But in code, these two equations are the crux of this entire problem. Let's see. There's two implementation of linear regression. One is from scratch. That means you do the math, you do everything basically. One is using scikit. Scikit is a sklearn library. It's a Python's library, which basically makes your job easier. It has an inbuilt function which you call it. It'll do the job for you. But to understand the concept properly, we do linear regressions implementation from scratch. Up until now, in the theory of linear regression, if you have any doubts, please go ahead. Any doubts? Feel free to unmute or put it in the chat box.
Could you please give small explanation about the two equation? What is
these two equations?
Yes, please.
Yeah. See, the cost function, as Varsha explained, the cost function tries to quantify the error in your line of best fit, and you're trying to somehow minimize this cost function. That is basically the concept. No, if you try to fit some curve, it should give me the minimum error. And now for this linear curve, basically. I'm trying to minimize this. This function has two independent variables. One is intercept, one is slope. I'm trying to take the gradient of this function, this cost function per se, with respect to my intercept and with respect to my slope. I will get something of this sort. This is, look at, how do I explain this? This equation is the important, this thing is very important. This theta j, theta naught is your intercept. Theta 1 is your slope. So theta j is equal to theta j minus alpha of gradient descent with respect to that variable, not gradient descent, partial differentiation of that cost function with respect to that variable. And alpha is your hyperparameter, which is learning rate. So when I differentiate this cost function, I am getting this term when I differentiate it with respect to theta naught. And I am getting this term when I'm differentiating with respect to theta 1. It is basic simple math, simple differentiation. If you do something of this sort, you will end up with this equation. And you multiply it with alpha and you subtract it. Depending on what this is or what sign this is, basically it will move in that direction, it will move in the opposite direction. That is how this is called. These are called updation equations. I think it is pretty common to call them updation equations. Are you clear with this, or is there anything else?
Yes, clear. Thank you.
Okay. Let's move on to the implementation now. We're importing 3 libraries: Pandas, Matplotlib, and NumPy. All 3 of them basics. Session 1 and session 2, we have seen what is happening. There is a dataset called data.csv, which has a bunch of points, basically x and y. I'm reading it into this data and I'm taking x and y values, which somewhat looks like this. And I'm trying to fit a linear curve through these points. How to do it? I'm defining these two as my hyperparameters. Hyperparameters in the sense these are parameters which I can control, which I can say, I can tell this to be 100, I can tell this to be 0.05. I can tell whatever I want, but I'm choosing these particular numbers because I know that these give me plausible results or acceptable results. So number of iterations in the sense I'm running for these many iterations, and LR is alpha. LR is basically your alpha, which is also known as learning rate. And I'm initializing my slope. The curve I'm considering here is y is equal to mx plus. M is my slope, C is my intercept. M I'm initializing it to be 0, and C also I'm initializing it to be 0. These are 3 lists which keeps track of the cost function, keeps track of my slope, keeps track of C. That means it updates the list based on how my M, C, and cost function values change. We will see why I've done this later on in a bit. I'm starting a for loop which runs from 0 to number of iterations, which basically runs over the iterations. Ypred is my predicted value of the output. Initially, it gives me a value of 0. Then the error function, this is the error. Error is basically ypred minus y. Y predicted minus the actual ground truth value. The cost function is half of mean of the error square, which is this basically.
Can you hear me?
Yeah, I can hear you.
Can you just zoom in a little bit? People are unable to see the text.
Yeah, sure. Is this better?
Yeah, this looks good.
Should I zoom in a little bit? Okay. Fine. I'll explain error again. Error is predicted value of y minus the actual value of y. And the cost function is half of mean of this error square, which is this equation. That is how the cost function is defined. Now, what is m derivative and c derivative? We have seen that this is my updation equation. Theta naught is equal to theta naught minus alpha of whatever that is. This particular part, I'm defining it as c derivative. And this part, I'm defining it as m derivative. I'm giving it a new variable name and I'm just assigning those values. So basically, m derivative is mean of y predicted minus y into x, which is mean of y predicted minus y into x. Similarly, for the value of c, it is mean of y predicted minus y. Y predicted minus y. That is m derivative and c derivative. And I'm updating this. This is the updation equation. M is equal to this is also similar to m is equal to m minus. I hope you know this. I mean, it's pretty simple. It's common programming knowledge. Yeah, this is same as whatever I've done before. And this m minus learning rate into m deriv and c minus learning rate into c deriv. This is my updation equation, which you see over here. This I will explain in a bit why I have done this. Let me run this code. It's giving me that my m value is this and my c value is this. That is how it is. If I plot this function based on the plotting functions you have learned just a couple of hours ago or something, this is how my line of best fit looks. This is for 50 iterations and my hyperparameter is 0.001. Now why I've chosen 50 is, I'll explain why. Since I've taken this history underscore cost to be my list, it keeps track of my cost function. It keeps track how cost function changes with respect to the number of iterations. So when my iteration number hits like around 15 or 20 per se, my cost function is stabilizing. This is a graph between cost function and number of iterations. Got it? So my cost function starts off very high, but after 15 or something, it kind of stabilizes at some point. So that assures me that after 15 iterations or 20 iterations, it is getting to converge and it is almost reached my minimum point. I have declared my m hist and c hist arrays over here just to keep track of m and c. This is to give us a cool animation. That's pretty much it. The animation, don't think about the syntax too much. Syntax is very cryptic. It basically uses something called as HTML display from IPython.display library. This is how my equation will change. This is how it starts off with 0, 0, 0, 0. Then it starts off with y is equal to 0 and moves. And after some point, it converges and it stays there. That is my line of best fit. This is how linear regression is implemented from scratch. So the basic crux of this thing is this updation equation. If you understand the updation equation, there's nothing else. It's simple code. Are there any doubts in linear regression implementation from scratch? Yes, I will give data.csv. Data.csv, the one used for Matplotlib is different from this. I will be giving it in a few minutes. Don't worry, I'll give it. Is there any doubts with linear regression implementation from scratch? If you have not been added to the WhatsApp group, we'll check on that later. Okay, I'm assuming there are no doubts. If yes, please do unmute and ask. Let's see how this is implemented using a library called scikit. This is very simple. I've written like 7 cells of code for this. For scikit, I've written only 1 cell. How it's being done is from sklearn, there's a sublibrary called linear model. From this linear model, I'm importing a function called linear regression. This is my data set. This is a different data set. This is completely random. This looks very distant and very disorganized. This particular data set. What we are trying to do is under this linear regression function, we are trying to fit a linear regression curve. This is the syntax to do it. This is how it's done. You pass an x comma y. Why I'm doing this reshape is this linear regression dot fit takes in a 2D array and a 1D array as an input. So I'm reshaping this 1D array into a 2D array. That is what this reshape does. Reshape -1, 1 does. Reshape can also do some other things, which you'll see later on. And this basically fits my curve. And if I call model.intercept underscore, it gives me the intercept. If I call model.coefficient underscore, it will give me the coefficient. That's it. That's all there is. And what is my predicted value of y? You can simply say ypred is equal to model.predictx. That means it basically gives the curve. Y is equal to mx plus c. That is what it does. So if I run this code, for this y is equal to mx plus c, if I pass in the values of this x, which is 6, 16, 26, 36, and 46, these are the values which I'm getting. And if we see it visually, Yeah, the data points are very disorganized. This was taken on purpose to show, even though the data sets are very far off, you can fit a linear curve through any type of data point. And this is how the linear curve will look. This is scikit's implementation. Are there any doubts? Any doubts? Linear regression is completely done. That is the entirety of linear regression. Next, we'll move on to polynomial regression. Any doubts you can ask? Okay, Archish, is it fine if we can take a 5-minute break? Like they can come back at 3:30.
Sure, that works.
Okay. Let's take a 5-minute break. We'll join back in 3:30 exact. I'll
Maybe
start off with
meanwhile, if you
polynomial
share the
regression.
data also.
Yeah, I will do that. I'm doing that now. Yeah. Give me a second. Yeah, the data set is put up in the chat box. Please do see that. Settle back in. I'll start in 1 minute. Okay, let's move on. Polynomial regression. What we have done now till now is linear regression. Linear regression is where we try to fit a linear curve through a data point, through a data set. What we are trying to do in polynomial regression is we are trying to fit a polynomial curve of particular degree, which we'll be deciding based on there will be some problems which occur due to in polynomial regression. In order to encounter these problems, we decide upon a particular degree and work with that curve. First, let's see what these problems are. The problems are overfitting and underfitting. Look at the first figure over here. Let's say my data set is these orange points and I'm trying to fit a curve. This here in this particular case, I'm trying to fit a linear curve. You see that it is the line of best fit, basically saying by reducing my cost function or changing my slope and intercept in such a way that the straight line minimizes cost function. Based on that, this curve is perfectly fine, but it does not capture all the features of the data set. Whereas in the second case, it captures the right amount of the right amount of features in this data set. That means if I give it a new point, it will be able to predict fairly accurate. In the third case, it captures too many features of the data set. That means it is considering every nook and cranny of this data set. This is known as overfitting. The first case is known as underfitting. Underfitting is also known as high bias. Overfitting is also known as high variance. We'll talk about what bias and variance is in a bit. Let's take an example to go a little more deep into this. Let's say the blue and green points are my data set. In these, I will choose my blue points to be my training data set and the green points to be my testing data set. From visual assessment, I can say that this saturation type of a curve is the line of best fit. That means it takes in the necessary features and only the necessary features. It doesn't take in more features or less features. What if I try to overfit? That means I try to pass in this red curve, which takes in every nook and cranny of this data set. It passes through every point of this data. Then when I'm passing my training data, which are these green points, they are very far off. You see when this red data set, if this red dotted line is my model, then for this testing data, it is not predicting the right values. They are very far off. This is the problem of overfitting or high variance. In this case, if I try to fit a linear curve, it is the line of best fit. Yes, that is 100% agreed. But it doesn't capture many features of the data. When I given these green
Shrikar?
points, they are a little far off.
Shrikar, can you hear me?
Sorry, is there any doubt?
No, this is Varsha speaking. Yeah, your screen was stuck for a while. Now it's fine.
Oh, my bad.
Yeah,
Oh, sorry. Can you see the figures properly again?
yeah. Now the
I
graphs are
hope you
visible.
can. Yeah, fine. Fine. I'll move on. See the linear curve, it is the line of best fit, but it doesn't capture many features, as many features as it should. And the red dotted line, it captures way too many features. That is why it predicts the model wrong. So now the problem at hand is we need to find a sweet spot between this linear type of a curve and a very high degree polynomial, which captures way too many features. We have to find a polynomial degree which is somewhere in between, and it tries to capture only the necessary features. This is where bias variance trade-off comes into picture. What exactly bias is? Bias is the error or the predictive error which shows up when there's a model which is too simple and it doesn't capture many features of the data. Let's say these are my data points. This is a new set of data points. And if I try to pass in a linear curve, it has high bias.
Shrikar.
That means there's way too much error because the model is very simple. Is there any
Shrikar, can
doubt?
you hear Atrish? Yes.
Yeah. So basically,
Yeah.
could you just brief over it again? Like someone wants you to brief over it again. Maybe just go through the last
Sure.
point. Like
Sure. I'll do that. What is the case of underfitting and overfitting? My green points are my testing data set. Blue points are my training data set. In the case of overfitting, I'm trying to capture way too many features than I need to. That means it passes through more points and it tries to take in more similarities and more than it needs to, basically. This red dotted line is a curve of overfit. And when I pass in my testing data set, I mean the green points, the testing data set, it doesn't perform very well. It gives me wrong outputs. This is my output if this model is being passed for this particular point, for this particular value of X, which is wrong. This is the case of overfitting. And in the case of underfitting, I'm trying to fit a simpler model, which doesn't capture any features of the data, any or very little features of the data. This is the case of underfitting. So we have to find a sweet spot between underfitting and overfitting. You can understand it better using this bias variance definitions. Bias is the error in predictive data and error in prediction when the model is too simple. Let's say when the model is degree of degree 1, whatever this error is corresponded as bias. It is referred to as bias. And when the model is too complex, that means it captures way too many features. It is called high variance, or this phenomenon is related to variance. This third picture is the case of high variance. The first picture is a case of high bias. And the second picture is a case of best fit. Whenever there's a degree, whenever you're trying to fit a polynomial of higher degree, you will face high variance. When you try to fit a polynomial of lower degree or lesser degree of degree 1 or say degree 2, then we face the phenomenon of high bias. Bias and variance are substitutes to each other. When there's high bias, there's low variance. When there's high variance, there's low bias. This is the concept of bias and variance. When we start off with a model initially, and we start off completely random, we start off with high error in validation and training. Let's say I'm dividing my data set into two parts. One is training data and validation data or testing data. The training data and validation data starts off very high because you're fitting a random curve, and based on your cost function, the cost function here also is defined in the similar manner as linear regression. We'll come to that in implementation. This cost function will decrease over time when our coefficients are changed, or let's say our curve is y is equal to a0 plus a1x plus a2x square dot. This a0, a1, a2 are updated based on how cost function is differentiated, or how basically gradient descent. This training error and validation error starts off high. This is the case of underfitting. And the training, as and when my iterations increase, or as and when my, not iterations, as and when my degree of polynomial increases, the training error keeps decreasing. This is because my model is trying to capture more and more features of the training data. There will be some polynomial of a particular degree which captures minimum validation error. This is the sweet spot we try to find. This is where my model captures only the necessary features and it doesn't overfit or underfit. That polynomial degree is my curve of best fit. This is what we try to find. And if we increase the polynomial's degree more higher and higher, the training error will obviously decrease because it is taking in more and more points into the curve of the training data and leaving out the testing validation data or the testing data. This is the case we have seen over here. This is overfitting. So initially your model starts with underfitting. Later on, it will find the sweet spot, and as and when you keep increasing the polynomial's degree, it will go to overfitting. This is the theory of polynomial regression. Now we'll move on to implementation of polynomial regression. Varsha will take care of polynomial regression. Before that, do you have any doubts in polynomial regressions theory? Any doubts in polynomial regressions theory? With implementation, I think you will understand it more clearly. Up until now, any doubts you can ask. Okay, then we'll move on to implementation of polynomial regression. Varsha, go ahead.
Yeah, so let's begin with the implementation of polynomial regression. Here we'll be using sklearn to implement polynomial regression. So as you can see, we have
Varsha, 1 second. There's a doubt. Varsha, 1 second. There's a doubt in the chat box. How to find the correct fit? Like when to know we stop? That is where visualization comes into picture. You plot the data set and see which degree polynomial gives you the best fit. We will be going through that in the implementation. You will see where the best fit comes, where not, where the best fit won't come. It depends on you, basically. You try out various stuff, and wherever you find the best curve of fit, whichever polynomial captures the necessary features, you stop there. You can quantify it also, but quantification will have complex equations. We'll see that in the implementation. You get to know that. Go ahead, Varsha, continue.
Yeah. So coming to implementation part of polynomial regression. So as you can see, we have imported NumPy and Matplotlib, and we have used two of these commands. You will know what polynomial features is with the example. So yeah, here coming to the code. So here you have X and Y are the inputs. It's a basically you know what this code is. This command is basically generating random values. Excuse me. Yeah, so it is generating random values, and Y is again it is also you just randomly provide equation so that it generates uh, Y values. And later on coming to polynomial features. So here what polynomial features does is it takes in the array and it creates a 2D array with values of the coefficients of x raised exponentially. Like you'll have a 2D array with the values of x, x square, x cube, x power 4, wherever you want, you wish for. So here we want it till degree 3. You can choose degree 1 or 2 or 3 based on, again, this is related to overfitting and underfitting, which we'll be seeing later. So I chose degree 3 here. So we'll be having using polynomial feature command to get a 2D array. So later on, I have assigned the values for a naught c. A naught here will be the intercept, and a1 will be the coefficient of x, a2 will be the coefficient of x squared, and a3 will be the coefficient of x cubed. So I've assigned the values for the coefficients of the graph that I'm about to plot. And this entire, you will know this, you should be knowing by now. This is the code for plotting the graph. And when you plot all of this, you'll get a graph something like this, a curve. So this is basically, you're trying to fit as many, the red dots denote the data sets, data points, and the graph is what you've plotted with the cubic equation. So this through this you can see that most of the points data sets are included within the graph. And so we can, this is basically just how you implement the polynomial regression. So now let's see how bias and variance works, and how underfitting and overfitting makes a difference. And moving ahead, so basically here I'm trying to, this is the code to get the data sets. Basically you just plotting them on a graph, data sets yeah, so this np.random.normal, it's generating random numbers, and you plot the graph with the data set, and this is how it looks like. And after that, we'll be using in this code, you are using a linear graph. You're plotting a linear equation here with degree 1 second. So yeah, so here you'll be plotting the linear graph, and here this is how it looks like. So you can clearly see that it's underfit. Most of the data sets are not covered in the curve that you've plotted, so which will lead to having higher basis. So this is how it happens. And later on, again, for the same data set, if you're trying to plot with degree 2, you'll see that the graph somewhat looks like this, which is again, you do not cover most of the data sets clearly. So let's move ahead, and we'll go ahead with degree 4. And again, here you can see that at least like most of the data set points are lying on the curve that we have plotted. So this might be a case of, where you'll see that, okay, so this might be the correct fit, right? So how do you know that? If you move ahead to degree 10, suppose. So when you go to degree 10, you'll see that it's most of the points are fit, and its variance is high. So this is a case of overfit, right? And if you go for, say, power 20, and again, you'll see a lot of variance compared to the previous ones. So which leads to overfitting, which is also again not a good way of training the model. So this is basically what variance and basis does. So when you are overfitting, it's not good. When you're underfitting, it's not good. So based on visualization, you can say that with degree 4, it will have the best fit. I think, yeah, that is all. This is all of these codes is basically plotting the graph and all of that. So it's not really important right now. Only thing that you need to know is the difference, the importance of having the how the degree matters. That is all. And explaining what underfit and overfit fitting looks like. So if you have any doubts regarding underfitting, overfitting, you can ask, and the implementation part of polynomial regression. So I think there are no doubts asked. So after this, we'll be going to logistic regression, and I think Priyanka will take from here.
I have a doubt.
Yes.
I'm audible. Hello.
Yeah, go ahead. Go ahead. You're audible.
Yeah. Wait, is there any situations where high bias or high variance is required?
Actually, there are some situations. So let's say I'll give you one good example. So when you want high variance is probably a situation where you have very less data. And let's say you want to do something like facial detection. Okay. You certainly don't want to go wrong, right? So you want to detect faces properly. So that is a case where you want high variance. Similarly, you can have cases where you might prefer high bias, but that is not usually the case.
So which one is better to achieve?
So neither. So you have to trade off between both. So you have to train your model such that it is actually the best fit and not underfitting or overfitting.
Okay, thank you.
Sorry, Priyanka, go ahead, please.
Can you see my screen?
Yes, maybe if you could slightly zoom in a bit, it will be helpful.
Yeah, okay. This is better?
Yeah, this is fine.
Yeah, okay. So starting off with logistic regression, until now we saw linear regression where we basically used a function, a polynomial function to fit the data. But here in logistic regression, we are going to use an S-shaped logistic function, which is a sigmoid function, essentially an exponential function of 1 over 1 plus e raised to minus z to fit the data that we have. And also in the linear regression model, we use the ordinary least square method for parameter estimation. Here we'll use the maximum likelihood estimation. The maximum likelihood estimate is that set of regression coefficients for which the probability of getting the data we have observed is maximum. So here we can see that we have used an S-shaped logistic function to fit the data that we have. And also logistic regression is different from linear regression in a way that in linear regression, we get our output values ranging from negative infinity to positive infinity. But in logistic regression, we get the values in like categories saying like true or false or 0 or 1 according to how we need them. Moving on to the types of logistic regression, we mainly have three types: binary, multinomial, and ordinal. Binary is the categorical response where we have only two possible outcomes. It can be like spam or not spam, true or false, 0 or 1. And multinomial logistic regression is just the same with three or more categories where we can either have like what sort of food is preferred by someone like veg, non-veg, or vegan, or naming different types of fruits like bananas, apples, pineapples. And ordinal logistic regression is just multinomial regression with a little hierarchy in it, where we can probably do ratings of movies from 1 to 5. Okay, so why should we use logistic regression over linear regression? There are mainly two reasons. First is that linear regression gives us the predicted probability ranging from negative infinity to positive infinity. And analyzing such a huge data, like data ranging, having such a big range is kind of difficult. So having logistic regression where we get probability ranging from 0 to 1 makes it easier for us to analyze it. And also when we have outliers, there's like a considerable effect on our model because of these outliers when we use linear regression. Like we can see here in the second diagram, there is a single outlier to the right, and therefore the entire graph is skewed to the right. And the linear model that we have used barely, like, doesn't even pass through half the data points that we have. And this is due to the outlier that is there in the data. So we don't want, this is an inaccurate model because it doesn't even take into consideration half the data point. So to be able to overcome this like inaccuracy, we use logistic regression, which basically tries to fit all of maximum of the points and solves the problem of the outliers. So for while using logistic regression, we use the log-odds function or logit function. There are multiple names to this function. The logit function is basically log of p of x upon 1 minus p of x equals to beta naught plus beta 1 x, where beta naught and beta 1 are parameters. It can, this is here I've shown a linear polynomial beta naught plus beta 1 x, but it can be anything like of higher degrees too. It doesn't have to be a linear one. So also here we use logit function where values more than 1 are less than 0 are not like given, because it's kind of trivial to get those values. Essentially, if you have values less than 0 or greater than 1, they just mean that the values are 0 and 1. So we use the logistic function to take care of those values also. And here we can see that after running our input data through a normal linear polynomial or a higher degree polynomial, we then run it through a sigmoid function, which is an activation function, to get output data values ranging from 0 to 1. Now, for us to be able to divide all this data into different categories, we use something called as the decision boundary. The decision boundary essentially enables us to understand that if for the given data, what sort of data falls under which category. Like as we can see in this diagram, there are green and blue dots like spread across the entire area. But for us, like some green and we have considered the blue line as our decision boundary. Even though we have green dots that cross the decision boundary and go into the blue, like we consider the maximum possibility and therefore like find the decision boundary to consider like now that every point below the blue line is not admitted and every point above the blue line is admitted. So here we have a linear line, like we have a linear graph, but it's not necessary to have the decision boundary linear. If our suppose function is circular, like x square plus y square equals to 1 or something, we can have a circular decision boundary too. So for sigmoid function, usually we can use decision boundaries that say that if our output value is greater than 0.5, we consider it as 1, and if it's less than 0.5, we can consider it as 0. Like linear regressions, even logistic regressions have cost functions that basically help us improve our model. But the problem with using the mean square error method here, which we used in linear regression, which was essentially the difference between the predicted output and the actual output, cannot be used here because our logistic function, which is a sigmoid function, is a non-convex function. It's like once we use the mean square error method on this, we get a non-convex graph, which is like, as you can see here, it's a weirdly shaped graph with multiple minimas, and the model is not able to like figure out which is the global minima, and therefore it might get stuck in a different globe, like a minimum, and cannot come out of it. And basically we can't get our best model, like we can't train it to the best possible because it cannot understand if it's in a local minima or a global minima. So to overcome this problem, we use another different loss function called the cross entropy function loss function, which first like essentially takes into account two cases for us when the predict like the actual output is y equals to 1 or y equals to 0. For when our y is equal to 1, we have our cost function of minus log of h of x, and when y is equals to 0, our cost function is minus log of 1 minus h of x. So here we can see the graph for when y equals to 1. We can see that the cost function is essentially telling that if our predicted output is also y equals to 1, then it's predicting perfectly accurately. So our cost function is 0. But when suppose the expected outcome is 1, but our model gives the outcome as 0, the error is like 100%. It's completely off. So here our cost function tends to infinity. Similarly, for when our y is equals to 0, like our actual output should be 0, but and our predicted output is 0, the cost function says that our cost or our error is 0. But if our model says that the value that we get is y equals to 1, then the error tends to infinity. So we can combine both of these functions to get a generalized function that considers all values from 0 to 1. And the cost function for a logistic regressor we get it of the form cost of hx equals to minus y log of hx minus 1 minus y log of hx. So this is how we get it. And like in a linear regression or a polynomial regression, we train our parameters using the gradient descent method, where we essentially find the gradients and accordingly change or optimize our parameters. Here, theta, like alpha is our learning rate, and this term in the sigma is our gradients. This term might look similar to the one used in the linear regression, but note that here hx is not a linear, like polynomial function. Hx is an exponential function over here. So this is all for theory. Now we move on to the implementation. Here for the implementation, I'm going to be using PyTorch. So PyTorch is basically an optimized deep learning tensor library based on Python and Torch. In machine learning, we need to represent data a lot. So we use tensors, which is basically a container that holds data in multiple dimensions. Because as the complexity of a model increases, it moves into it becomes multi-dimensional, and for that we use tensors, which can be like numbers, vectors, matrices, or multi-dimensional arrays like NumPy arrays. Also, PyTorch has multiple modules that are used to represent neural network and has like a really important functions in it. Some of them are AutoGrad, NN, and Optim. The Optim module is a package with pre-written algorithms for optimizers that can be used to build neural networks. And NN model includes various classes that help to build neural network models. Also, all models in PyTorch subclass use the NN module. Moving on to the actual implementation of logistic regression. Here, first, I would like the steps basically used in this implementation is that we're going to prepare our data and then also create a model, then generate loss functions and optimizations, and then accordingly train our model in 3 steps, that is a forward pass, a backward pass, and accordingly update our weights and parameters. So first, we would import all the necessary libraries. We import Torch for the neural network modules and sklearn for datasets, and NumPy we import so that we can do data transformations on the data that we're using. Standard scalar is basically used so that we can transform a data such that the mean of the data is 0 and variance is 1. And also train test split here I've used so that we can train our data and also check for the accuracy of our data. Train test split basically divides the available data into like 2 parts. One part that we'll use for training and the other part that we'll be using for testing. So here, while preparing data, first let us load the data. Here we've used the breast cancer data, which is essentially according to the data that we have, predicting if the person has breast cancer or not. And first, then we'll see the number of samples and number of features that are there. Here we can see that we have 569 samples and 30 features. And the next step here we've done is that we've divided the data into training and testing data. Test size equals to 0.2 says that we've basically divided the data such that 20% of the entire data is used for testing. And random state equals to 1, 2, 3, 4. Here 1, 2, 3, 4 is an arbitrary number. You can take any other than 0 to say that basically divide the data randomly so that there is no bias while training the data such that there's a different data for training and a different data for testing. And then there's like basic data transformation that will help for future, like later commands. So we've done standard scaling, and also we've changed the data type from double to float 32 in the later steps for the training, testing, and X and Y. And also the Y train and test, we've basically changed it from a row matrix to a column matrix. Now moving on to the model, here I've created a class which essentially includes the linear regression that we've taken from the NN module, and also a sigmoid function. Here in the linear regression, we're inputting n input features, which is essentially 30 features that we saw, and giving a single output that is Y predicted. And also, after we use this linear regression, we're going to run it through a sigmoid function. After that, we are doing the loss and optimization. Here, my learning rate is 0.01. This is a hyperparameter and I have set it to 0.01, but you can change it according to your model. And my criterion is BCE loss, which is essentially the binary cross entropy loss that I mentioned before. And for my optimizer, the optimizing model that I've used is SGD, which is stochastic gradient descent. Till now, we saw the gradient descent, where we considered every single parameter for every single data point. Now, for very complicated models, we have like thousands of data points with thousands of parameters. So the calculation for a single step goes into millions. So to reduce the training time that's required, we use stochastic gradient descent, which essentially says that we would consider only a few parameters for a few data points. That is, it cuts down on the number of parameters it takes for every data point. So that's why a stochastic gradient descent is usually preferred for really complicated models. And now the training loop, where we train the model. First is like I've selected my number of epochs to be 100, which is again a hyperparameter. You can like take any according to your model. And then the forward pass is where we essentially move pass the training data set through the linear model and then through the model which includes the linear regression and also the sigmoid function. and then we calculate the loss for the output that this model gives us. After calculating the loss, we do the backward pass. Loss.backward is a function, it's an inbuilt function where the library does all the work for you. It calculates all the gradients for you. And after that, from these gradients that we have calculated, we optimize our parameters using the function optimizer.step. The next step that I've done is optimizer.zeroGrad, which is essential here because loss.backwards is a function that works such that it keeps on adding the gradients that it has calculated till then. So what would happen is as I iterate through this loop, my gradients will be added up, which I don't want. I want fresh gradients for every iteration. So therefore, I have to set the gradients back to 0 after every iteration. Just to see, 1 second, let me run all these cells. Yeah, so just to see if my model is getting any better after every epoch, I'm printing the loss of the model, like loss here after every 10 epochs. So here we can see that the loss is gradually decreasing from at the 10th epoch, my loss is 0.5, which is a lot, to up to the 100th epoch, I have my loss as 0.239. After this, it's like here the training of the model is done, but just to see if we're doing any good with this model, let us check the accuracy. Here I'm using torch.nograd because here we don't want a model to learn through the data. Here the learning is being done through the training, and now we have to see if our model is doing well. So here we don't want it to update any gradient, so we are going to use torch.nograd. First, we're going to run the testing data set now on the model, which will run it through a linear regressor and then use the sigmoid function on it. And then next, we want to divide the given output into classes, which is essentially the where I said the decision boundary comes in. The dot round function basically tells that if your output is greater than 0.1, consider it as 1, and if your output is less than 0.1, consider it as 0. So here we get our outputs in 0 and 1, which can be compared to the outputs given in the actual data set. So here the next step is find the accuracy, where we compare the y test, that is the actual output in the data set, and also with the y predicted CLS, that is our predicted y, which we sum it over the entire data and divide it by the number of samples, that is the test shape that we have, to get the accuracy. And then I print the accuracy up to 4 decimals. So here we get the accuracy to be 0.886. This accuracy is pretty good, but we can make it better. Like we can get better accuracies in this model by kind of for like playing along with the hyperparameters that we have, like the learning rate or number of epochs or the optimizer that we use. So that's how we implement a logistic regression. And anyone has any doubts, feel free to ask them. Okay, so basically the round function divides the output that we have into categories, that says like all the outputs that we get that are greater than 0.5 will be considered as 1, and all the outputs less than 0.5 will be considered as 0. It sets a decision boundary there. Okay, so the purpose of using standard scalar, like scaling it to 0 mean and unit variance, is that it's easier to handle data that are like similar in the range. So Sometimes we'll be having data in the thousands, like values, face values in the thousands. Some data will be like in just one digit numbers. So our model kind of can get confused between the importance that different parameter, like data sets, different features have while training it. So for this to not happen, we scale all the features that we have to a single range so that the model doesn't have a bias towards higher valued parameters, sorry, features.
Maybe I'll give you a small example. Let's say you take temperature and you measure it in Kelvin as well as Fahrenheit, right? So basically, when you use a standard scaler, like the temperature that we measure using Kelvin as well as the temperature that we measure using Fahrenheit will be in the same distribution. So there is like a fixed conversion between Kelvin and Fahrenheit, right? So basically, your standard scaler like takes care of that and brings both of them to the same distribution. I hope that made sense. Okay, great. So are there any more doubts? Okay, looks like there are. So basically, on Monday, we'll be again resuming with a few more machine learning models. Namely, we'll be looking at simple vector machines and naive Bayes. So we'll be our next session will be on Monday at 2 p.m. Also, I think you might. Sorry. Okay, so I think that was a mistake. So as I was saying, our next session will be on Monday at 2 p.m. where we'll be covering a little bit more about ML models and how they work and implementation of them. Also, you might know that the task is due on Monday, so please have a look at that. And if you have any doubts, please get back to us on the group so that we'll be able to clear any of those doubts also. Okay. So
Yeah, Archish.
yeah, sorry, go ahead. Someone was saying something.
Yeah, can you hear me?
Yes, please go ahead.
Yeah, to understand about this regression analysis and all, for a ML machine learning, we should have any mathematical background, any specific topics or.
Actually, no, not required. It's just like logic that is there. So basically, understand what is a linear function, that is basically something like y equal to mx plus c, and how a quadratic loss function behaves. Basically, that is your mean squared error. If you understand both of these, that is more than enough to understand how a normal regression works. So in the future, next week in one of the sessions, we'll be covering about the stochastic gradient descent, the simple gradient descent also, and also some other optimization. So we'll be looking at the math later on in the session. So right now you don't need any mathematical background.
Okay, thank you.
Okay, so I
Yeah,
think
thank you.
that is it. Okay, so I think that is it. We have planned for today's session. So we'll meet again on Monday. So I'll be sharing the recording, and the content for this session is already uploaded in the GitHub repository, so you can have a look at it. So yeah, so syntax is very hard. So basically, there is no need to remember the syntax. So that is all I would want to say. Like you can always refer to the documentation of each library. So if you want to do some, basically these sessions are to just guide you to say that, okay, there is something out there like this, so that you understand like what it is and how you should use it. And to remember the syntax and all, you can always look at the documentation. So if you see NumPy, PyTorch, or Matplotlib have a very good documentation available. So it's just a matter of searching what you want and you can find out how to use them directly. So you don't need to remember the syntax, definitely. Okay. Okay, so any other questions?